Okay, here we go with chapter 5. We're going to talk about the normal model right now. So I want to begin with the fact that the normal model refers to a picture that is unimodal and symmetric. So this would then be quantitative data only. All right, so the normal model literally is kind of representing, I like to draw this picture here, that unimodal and symmetric picture that we try to draw and we try to make look perfect every time, but we're not all capable of doing that. Well, I try to make it unimodal and symmetric as best that I can. And remember that way back in chapter 2, right, we said that, or 3, I don't remember, but we said that the center here would be the mean because it's unimodal and symmetric. And the spread, if you guys recall, would be the standard deviation. And this was x bar, and this letter was sx. So what we're going to learn to do is kind of like draw this picture, okay? So, whoops, I just zoomed in. So what we want to do is put the mean smack in the middle. So this is the x bar, or the mean, right in the middle. And what this picture does is it's actually perfectly symmetric. So there are 3 little tick marks on the left and 3 on the right. And they all go out the exact same amount, which is exactly 1 standard deviation. So here we go 1 standard deviation to the right. The second tick mark is exactly 2 standard deviations to the right. And the third is exactly 3 standard deviations to the right. And then we go backwards in the opposite direction. And we say, okay, well, if we're going to the left, then we're going to subtract 1 standard deviation to the right, subtract 2 standard deviations to the right, and then subtract 3 standard deviations to the right. And we end up with this beautiful picture just like this. And many of us have seen a picture like this before, referred to as like the bell curve, but this is also the normal model, okay? So one thing I like to do that ends up getting a little bit crazy is that I like to add a few axes underneath here. So when we talk about x bar and sx, these are Latin letters, letters from our alphabet, like our American English alphabet. So we refer to those particular values as being from the sample. So this would be really like sample data, okay? And we would write this, I'm going to write new notation. It's going to be big, capital N represents a normal model. I open a set of parentheses and I put the mean first, and then I list the standard deviation second. So literally it's a value, comma, another value. It's almost like I'm writing an ordered pair. And so I can kind of just write this information down if I know that if I'm looking at a normal model. I can kind of grab its mean and standard deviation that way. And sample data simply means that I collected it myself or somebody else did, and it wasn't kind of like provided for me from a large group. If it was provided for me from a large group, then I would have other notation, which is going to throw some of us off. So that large group would be your population data. And many of us don't like this because this means that we're using Greek letters. So this is the letter mu, which is an M in the Greek alphabet. And this is the letter sigma, which is the lowercase s in a Greek alphabet, standing for mean and standard deviation. So I want you to treat them just like you did above, where we have like the mean for mu goes in the middle, and then I still make my 3 tick marks on either side. And on each one of these, right, I go plus 1 sigma, plus 2 sigma. So I make this exact same picture, except I'm just adding whatever value was given from the population, okay? And then I repeat it on the back end. Minus 1 sigma, minus 2 sigma, and minus 3 sigma until I have a very similar picture above, right? The same image would be above, but the scale would be representative of now the population data. And then there's one other thing we can do, and that is to convert this. So I'm going to now talk about how we could convert this into the standard normal model, which is what we all want to see, right? We want a 0 in the middle and a 1 counting from either side to make our lives easier. So standard normal looks like this. 0 goes in the middle, and we do our best to make these evenly spaced, and we just count 1, 2, 3, minus 1, minus 2, and minus 3. So we have technically the exact same picture above. I never changed the curve, but I have 3 possible ways to label this picture. I'm either given some sample data, or I find it myself on the calculator. I find my X bar and my S. Maybe somebody gives me population data, or I'm told this is a standard normal model and I can make my picture with a 0 in the middle. All right, so let's keep going because we want to talk about how we can figure out what standard normal is. So there's standard normal is like when people say they're standardizing something, okay? These are standardized scores. The other way that we refer to them in this class is as z-scores, okay? So the standard normal model and z-scores are actually the same exact model. So over here, I'm going to write the formula for a z-score because it's actually incredibly important that we remember how to calculate this guy. We would take the value that we are given from the table, subtract the mean, and then divide by the standard deviation. So X is the data value, X bar is your mean, and SX is the standard deviation. Okay? So z-scores here are computed so that we can kind of transition things that aren't on the same scale into things that are along the same scale so we can then compare them. So z-scores are used. Z-scores are typically used in this class to compare unlike items. Right? So people always say, like, you can't compare apples to oranges, and I'm like, sure, standardize them, measure them in some standard form, plop them on the same scale, and I'd be happy to compare them for you. Okay? I'm a numbers person. Literally, show me the information and I will compare them for you. Okay, off my soapbox. So now, right back to our standard normal scores, there's only one more note I want to make, and that's that z-scores actually have measurement units, and they are measured in standard deviations. So you see how we're dividing by the standard deviation? That means that the z-score measures the number of standard deviations something is away from the mean. So it's literally telling me a count of standard deviations away from the mean. So let's go back to this little picture because I'm going to draw all over it, my standard normal, because this is going to be true of any. Whoops, that was terrible, but we're going to go with it. We're going to talk about now any normal model, but all of us probably prefer looking at it like this without all the crazy notations, okay? So now we're going to talk about what's referred to as the empirical rule. And I'm going to use some fancy colors here because I really feel like this is best understood if we make this picture as understandable as possible. So what I'm going to do is I'm literally going to like divide this picture up. So if I look just between -1 and +1 standard deviations away from the mean, then that contains exactly 68% of my data. And now if I jump out and I say go to -2, right? And +2, and I bring this here out a little bit further, then in between -2 and +2 standard deviations away from the mean, that's 95% of my data. Okay, and we're gonna go some other color, blue, and we're gonna go 3. I'm just gonna draw a line down here because I can't really fit a dotted line there. And if I take this out 3 to the left, so -3 and +3 standard deviations away from the mean, then there's 99.7% of the data between those two values. So 68% of the data lies within 1 standard deviation. 95% of the data lies within 2 standard deviations, and 99.7% of the data lies within 3 standard deviations from the mean. So notice that I never stopped my lines, like my picture never quite meets that scale that I've labeled, because this picture does go on forever. We never said 99.7 is when we stop, right? We're going to keep on going, and this picture is going to keep on measuring. And you might be asking, like, what if I don't know that something's exactly 1 standard deviation away from the mean? Well, I'm going to show you in the next video how to do your calculator commands for this particular chapter. So watch in the next video for how to work the calculator here.